Hi class, in this video we're going to be talking about 2.2 and 2.3, sets and set operations. And now in the textbook, section 2.2 introduces sets and kind of basic ideas of elements of sets before starting to introduce things like the union or the joining of two sets and the intersection or taking what's common to two sets. And then in 2.3 it talks about other ideas like the complement and the minus operation, as I'll call it. But I really think that the two ideas are close enough together that it's just worth talking through them together. And so this video will cover both of these sections. So sets and elements. So by convention, we're going to use a capital letter to denote a set. So capital letters denote sets. And lowercase letters denote elements. So here, A is the set of letters in the English alphabet. And so S, for example, is an element of A. And that's behind my face. So S is an element of A. So A is a set or some collection of elements. And the things in these braces, so that's these here, our opening brace and our closing brace, show kind of the limits of our set, and everything between it are elements of that set. So to say that something is an element of a set, we use this kind of E-looking symbol. So here we say T is an element of A. T is an element of A, and so we'll use ELT as an abbreviation for element. And we'll read it as T is in the set A. So T in A, or T is an element of A. And so A isn't just any old set, it's the set of letters in the alphabet, but not just the alphabet, it's the English alphabet. So if we just said the alphabet, it's like, well, do you mean the English alphabet, the Spanish alphabet, right, which has our Aye and our Enye, our Che, or what do we do if we were talking about, say, the Greek alphabet, alpha, beta, gamma, delta, right? There are lots of other alphabets. So sets need to be well defined. It needs to be clear what is in the set and what isn't in the set. So if we were to define a set, let S be the set of natural numbers less than 5. We have two different ways that we can denote that. The first is called roster method, and it's called roster because what we do is we just list all of the elements of a set. And our natural numbers, the natural numbers, which we draw with this fancy N, is the set of 0, 1, 2, 3, and so on. And so this N stands for natural numbers. But we can also use what's called set builder notation. Set builder notation is where we would say the set S is X, and I'm going to break this down on the next slide. The vertical line is such that X is a natural number, it's in N, and it's less than 5. So we have those two methods here, and this is where I want to break it down. So we read this as S is the set, curly brace, of all X, this vertical line means such that x is in n, or the natural numbers, and x is less than 5. So suppose we wanted natural numbers less than 7, natural numbers less than 7, we would let, if we call that w, for example, w equals the set of all x such that x is in the natural numbers and x is less than 7. And so we already know some sets. We have our counting numbers, 1, 2, 3, and so on. We have our natural numbers, which start at 0, so these are natural numbers. And it's really important to remember that 0 is included in our natural numbers. And then we have our integers, which is all natural numbers and their opposite. So for every 1, there's -1, 2, -2, and so on. So these are the integers. And then Q is the set of all numbers m over n such that m and n are natural numbers and n equals 0. Those are our fractions, or our rational numbers. I is the set of irrational numbers. So those are the non-terminating, non-repeating, non-repeating decimals. And R are the real numbers. So that is all of our rational and irrational numbers. So it's important now, that's not how I want to start that sentence, just to show you how we would draw each of these letters. So to draw this n for natural numbers, it's kind of like 2 7s. But really, our integers is really like a 7 and then an up to down 7. To make our Q, we draw a circle with a vertical line and then our Q mark. Irrationals is just like the Roman numeral 2. And our reals, we do two lines and then we draw our R. So we're going to be working with these sets a lot through this course, and so it's important just that it's easy for you to be able to write those. And so the name of this font is actually Math Blackboard, just so you know. So we can write naturals, integers, or natural, integer, rational, irrational, and real numbers. And we know how they relate. So we have all of our natural numbers here inside. We have 1, 2, 3, and so on. And then and I missed one, didn't I? 0, 1, 2, 3, and so on. Z adds to that our -3, -2, and so on in both directions. Our rationals give us our fractions. We have our irrationals, like the square root of 2, which can't be written as a fraction. And then our real numbers are just Q and I together. So let's practice a little bit with set builder notation. Use set builder notation to write the following sets. So here we have E equals 0, 2, 4, 6, 8, and so on. And so those are even numbers. So E is the set of all x such that x is in our natural numbers and x is even. And the same with our set down here called D, 1, 3, 5, and 7. D is our set x such that x is a natural number and x is odd. And now, that's a perfectly fine definition for that set. But sometimes we want to be thinking a little bit more algebraically, and we want a little bit more precision. So here we could say that E is the set of all x such that x semi-natural numbers, but really it's not x, it's our multiples of our real numbers, or of our natural numbers. So here, let me rewrite that because then I can say it again. E is our set of numbers of the form 2 times x, where x is a natural number. So we have 2 times, and remember, n, 0, 1, 2, 3, and so on. So we have 2 times 0, 2 times 1, 2 times 2, 2 times 3, and so on, which is 0, 2, 4, 6, and so on. Exactly what we wanted. And similarly, we could say D is the set of numbers of the form 2x plus 1 for every x in the natural numbers. And so here we have 2 times 0 plus 1, 2 times 1 plus 1, 2 times 2 plus 1, and so on. So we get 0 plus 1 is 1, 2 plus 1 is 3, 4 plus 1 is 5, and so on. And so we can either write it as x is in n and x is even, or we can write it as 2x, x in the natural numbers. And with odds, we can write it x is in n and x is odd, or we can write d is the number, is all numbers of the form 2x plus 1 for x in n. And so when we talk about even and odd numbers later in this course, I want us to recall these definitions for even and odd. They can be written as 2 times a number or 1 more than 2 times a number. And so there's a third way we could write it. It's all x, such that x is 2 times some number, and n is a natural number. And here x is an odd natural number. X equals 2n plus 1 for every n in n. So there are multiple ways we could define a set, and depending on our uses, we may want one or another. So let's think about comparing sets. So I have 5 sets here, P, Q, R, S, and T. And how can we compare them? Well, we can say that P and R look to be more or less the same. They both have A, B, and C. If we look at P and Q, we want to say something like they're the same size. They both have 3 elements, A, B, C, or X, Y, Z. They're not the same elements, but they're there. In terms of quantity, the same number. All of the elements of P are in an S, and all of the elements of Q are in T. And so let's get some terms for how we can compare sets. So equal sets, P and R, so those were the ones with A, B, and C, P and R. And so I'm going to jump back and forth. P and R are equal. P equals R because A, B, and C, A, B, and C. 2 sets are equal if they have the same elements. P equals R. Equivalent sets, and see, this is another reason why I don't like to use the tilde for not P, because here we use tilde for equivalence. So P and Q have the same size, but different elements. So if we look at P and Q, this A and X, B and Y, and C and Z, so P is equivalent to Q because they have the same size. And so why did we say it? Why did they say they had the same size? Because every element of P went to exactly 1 element of Q. And so the size of a set is called its cardinality. And cardinality is the number of elements in a set. And so two elements of the same cardinality are equivalent. And we can say that two elements have the same, or two sets have the same size if they have the same cardinality. So P, Q, and R all had the same cardinality. They all had 3 elements. And so we can also say, and this was my arrows, two sets have the same cardinality if there exists a one-to-one correspondence between them. So that means if every A goes to X, and every B goes to Y, and every C goes to some Z, and only one, and everything in Q is accounted for, nothing left over, and everything in P is accounted for with nothing left over and nothing double counted. So, two sets could have the same size. But can we have a set with size 0? Can we have a set with nothing in it? Take a moment and think about what would that mean if I have a set with nothing in it. Say, for example, let C be the set of 47-foot-tall house cats. I feel fairly confident in saying that there aren't any 47-foot-tall house cats. It can be well defined, but it would be empty. And so the set with size 0, that is a set with no elements, is called the empty set. And we use this 0 with a line through it. That's the empty set. And if C is my set of 47-foot-tall house cats, we could say that C is just an opening and closed brace. And so these two notations are equivalent. So we can talk about sets being equal if they have the same elements, ABC and ABC. We can talk about sets being equivalent if they have the same number of elements, but they're different, so they have the same cardinality. We could talk about subsets, and that's where every element of P is in S. And so let me jump back. So this says, to read this, P is a subset of R because every element of P is in R, but I would almost say that P is a subset of S. P subset S. Because A is here, B is here, and C is here, but there are more things in S that aren't in P. So P is a subset of S. Oh, and that's what it says here. I just have it typed up. So P is in S, P subset S. Now, proper subsets. A proper subset is if every element of P is in some set S, but there exists some element in S that's not in P. So let me P, R, and S. We had ABC, ABC, and A, B, C, D. So P and R are subsets, or P is a subset of R, and P is a subset of S. And so it is important to note that direction matters here. But we could also say proper subset is when everything of one is in the other, but there's more in the other. So A goes to A, B goes to B, C goes to C, but there's also a D. So there we say P is a proper subset of S. And you'll also see P is a subset, but not equal to S. And so those two are equivalent. And then to give you this other direction, just to give you another term, this is called superset. And it's actually a proper superset. And so this is a just superset. So you'd say P is a subset of R, or R is a superset of P, or P is a proper subset of S, and S is a proper superset of P. And so so we can talk about, and you can start to see how this gives you this notion of like bigger than, greater than, or less than, or greater than or equal to. And that's precisely why we're introducing this, because as we move on to the number systems and comparing numbers, it's going to turn out that equal sets correspond to our equals. Equivalent, that would be like 2 plus 3 is equivalent to 4 plus 1. They're not the same, but they have the same quantity. Subsets, so if we had some set with 3 elements and another with 5, we could start to talk about less than, right? And so these ideas build this foundation for us to talk about the number system. And so that's how we can describe the relationship between two sets. What about the intersection, the things that are common to both? So let's say A is here, and B is here, and this has A, B, and Z. And over here we have Q, A, and T. So A intersect B is the set of all X such that X is in A and X is in B. So there's an A and A, and there's an A and B. So there's an A. There's a B here, there's no B there. There's a Z here, there's no Z there. A Q here, but no Q and A, and a T and B, but not an A. So that means A intersect B, the only item common to both, is A. And now you can start to see why we might want an empty set notation, because if we had W and X, AB and ZY, W intersect X is the empty set. There are no elements common to both. And just like the logic tables, this is a lot of new terminology, but as you start to work with it in the homework and maybe revisit some of the examples in the textbook, this will become more familiar. Now, union is the set of all elements in A or B or both. And so if we have A and B, and we'll call that A, B, Z, and here we have X, Y, and Z. A or B is A, B, X, Y, and Z. And your elements don't have to be in alphabetical order, but I would say, sake of convention and ease, it doesn't hurt to put them in alphabetical order. But one thing that must not be the case, notice that there's a Z in both, but I didn't write it twice. You only ever write an element once. Because Z is a unique element. It can't be in there twice. If it's there, it's there. And if it's not, it's not. It can't be there twice. So the union is in A or B or both. But we don't double count. And now the complement are the sets that aren't in A, but are from the same universe. And so what do I mean by universe? Let's say we have my natural numbers. And inside that, I have my evens. And let's call that E. And we also have our odds, which are also in here. Now, if n is our universe, the complement of our evens is our odds. Because it's everything that's in our universe but not in that set. Or the complement of our odds are our evens. Because they're in the universe but not in that set. And so for complement to be defined, your universe, or the big set that we're working within, must be well defined. And then we have the minus. A minus B. So A minus B is all those x's such that x is in A but aren't in B. So let me give you an example. If I have A, B, C, D, and B is C, D, E, F, A minus B, and the fancy term for this is the complement of A relative to B, but I would say we're going to call it A minus B, is the set of all things in A that aren't also in B. So A is in A, but not in B. B is in A, but not in B. C is in A, but it's also in B, so we won't count it. D is in A, but it's also in B, and so we won't count it. And now there are more things in B, E and F, but that doesn't matter because all we're doing are the things in A, and then we take away anything that's in B. And so we'll call that A minus B. So in this case, A minus B is just that set, A, B. And now, a useful way to show this, and I maybe already started that with my one example, are Venn diagrams. And so I'll call them John Venn diagrams because I think it's useful to remember that Venn diagrams haven't always existed. A long time ago, a man named John Venn came up with these diagrams to denote the relationships of sets. And so when we do this, we have some circle that represents A and some circle that represents B. And then this part in the middle are all of those things that are in both of them. These things here are the things in B that aren't in A. And these are the things that are in A and not in B. And just like we can talk about A or B, the things that are in either, as long as our universe is well defined, we can talk about the complement. So those are the things on the outside. This part out here is not A or B, or the complement of A or B. And so I wrote these in on the previous slide, but so you have a nice, neat, clean copy. If this set on the left is A, and this is B, A take away B, and B take away are those outside partial circles, and that intersection is A intersect B. So a summary of what we've talked about. Sets are collections of elements, and sets have sizes. That's called cardinality, the number of elements inside. There are certain set operations we can do that we can use on sets. We can talk about the union, or putting two sets together, the intersect, or looking at only the common, the complement, so things that aren't in a given set. We can talk about the minus operation, where we take away the elements of one set from another. We can also talk about relationship between sets. We have subset and proper subset, and I also introduced superset and proper superset, right? And so I care less strongly about superset, but it's important we know subset, and subset looks like this, and proper subset looks like this, or like this, right? And so A union B, A intersect B, the complement of A take away B. And that's a lot of new material. But it's important that you look at the homework now and kind of get used to working with some of these ideas, particularly union, intersect, complement, and minus, subsets and proper subsets, because this is going to set the foundation for working with numbers when we talk about counting. We talk about the cardinal numbers, and then we're going to talk about union when we talk about addition, our relative complement or minus when we talk about subtraction, and we will revisit these soon. Have a great day, everyone.